Hello everyone, welcome to Prep Station Physics. Today I'll be taking you on the topic wave. I want to take on the topic wave and we'll quickly look at what is wave because sometimes there's this misconception on the actual definition of wave and how it relates to our present environment, and then we'll also look at how to describe waves. All right, so let's quickly start with the definition for waves. Let's see what wave is all about. Okay. All right, now a wave can be described as a disturbance that travels through a medium, transferring energy from one place to another. Now, consider the keywords, the ones that are highlighted: disturbance, medium, and energy. And then let's also consider spring and ripples on the water, okay, on the surface of water as example of a wave for this explanation. So that is to say, I'll be using two examples. One is the movement of a spring, also known as slinky, and then I'll be using the ripples formed on water. These are common examples that we can easily relate with. Now let's go back again to that definition. A wave can be described as what? A disturbance that travels through a medium. So we're going to look at what is disturbance, we're going to look at what is medium, and then we're going to look at what does it mean to transfer energy. All right. Now, let's look at this diagram quickly. Which of these is not an example of wave? Which of these is not an example of wave? Well, looking at these two diagrams, the first one is an example of wave, but the second is not an example of wave. I'm not looking at the formation lines on the sand, but I'm looking at the footprints. So the footprints you are looking at is not an example of wave, even though we have a repeated pattern. But the diagram on my left is an example of wave because here you have the water being troubled. Of course, that is disturbance. And something must have caused the water to be troubled. So let's move forward. Now, to introduce a wave into a spring, remember I told you I'll be using two examples. The spring, also known as slinky, and ripples on water. You know what ripple is? When you drop a stone on the surface of the water, the spherical pattern that forms is called ripple. So I will be using these two examples to explain what is wave. Now, to introduce a wave into a spring, the first particle is displaced or moved from its equilibrium or rest position. Now, equilibrium position is when the spring or the object that is about to exhibit wave has not moved, okay? Now, when you displace the first spring, what happened? For example, let's say a rubber band. If you stretch a rubber band and allow it, it comes back, all right? Now, if you have a spring and probably draw it or stretch it, what happened? It returns back. So that returning is called the equilibrium position. Now, to introduce wave into a spring, the first particle is displaced or moved from its equilibrium or rest position. Now, we have two diagrams here. The first one is an unstretched spring. The second is a stretched spring. Now, you can see the difference. If you stretch a spring and allow it, it moves to and fro, back and forth. Now, remember I told you to look at the keywords in that definition of waves that have been highlighted. The first one is disturbance. Now, the act of moving the first coil of the spring in a given direction and then returning it to its equilibrium position to create a pulse is known as what? Disturbance. An unstretched spring has no problem, but once you stretch it, you have created a pattern known as pulse. And that pulse is what is called disturbance, okay? So that disturbance in that medium create what is called wave. Now let's move forward. A pulse is a single disturbance. So if I stretch a spring once and allow it to return, that is a pulse. But if I do that repeatedly and then allow it to continue moving back and forth, then it becomes what? A disturbance. and that disturbance is able to create what is called wave. Okay, remember I told you wave is what? A disturbance that travels through a medium. Now, the repeating and periodic disturbance that moves through the medium from one location to another is referred to as wave. I'm still trying to explain what is wave, okay? Now, the repeating and periodic disturbance that moves through a medium from one location to another is referred to as wave. Now, what is a medium? You might want to know, because in my definition I said wave is a disturbance, right? I've explained what is disturbance that travels through a medium. Now, what is a medium? Medium here refers to matter. Remember, we have three states of matter: solid, liquid, and gas. So that means wave can travel through solid. As an example, sound waves can travel through solid. And then we have liquid. Sound waves can travel through liquid as well. Even gas, depending on the temperature. So the medium here is the substance or material that carries the wave. For example, water. When you disturb the water and create ripples, that ripples is able to transfer energy. And if there is any object on the surface of the water, what happens? It will start shaking. It will start moving. And of course, according to Newton's law, an object will continue to stay in one place of rest until a force is applied. So for that object to move on the water, it means there is a force and work has been done. Now, where is this work coming from? From the wave that has created disturbances in the medium. Okay, I hope you got that. Now, to introduce a wave into the spring, the first particle is displaced or moved from its equilibrium position. Okay, I've explained that before. Now, let's move forward. Now, the second example I said I'm going to be using is ripples and water. Okay, I said I'll be using two examples. So the second example is ripples on water. Now, to introduce a wave to a pool of water is very simple. This is what we do every day, and we experience it every day. Just drop a tiny stone on the surface of water. You will notice something. And what is that? This will create a pulse. Remember, I differentiated between a pulse and disturbance, okay? A single drop of stone will create a pulse, but if you do that continuously, thereby, and it becomes a repeated pattern, then it becomes a disturbance. And that disturbance is what we refer to as wave, because that disturbance will come into the medium. The medium in this case is the water, to create what? Energy that will move, that will be transferred from one point to another. Now, this will create a pulse as seen as a circle on the surface of the water. We do this every day. It's very simple. Just drop something on a pool of water, even water in a bowl. You will see spherical wave pattern form on that surface. Now, this will create a disturbance which is seen as ripples on the surface of that water. Remember, I'm still trying to explain or to describe what wave is all about. Now, these ripples on the surface are known as waves. Let's move forward. Now, we can describe wave motion in terms of 1, material for propagation, and then number 2, direction for propagation. So I'll be describing wave in 2. 1, when we consider the material for propagation, and number 2, when we consider the direction of propagation. Now, what does this mean? Let's start with the first one. Now, under material for propagation, I will be talking about 2, and that is number 1, mechanical waves and electromagnetic waves. I'll say that again. So, description of waves under material for propagation, I'll be talking about 2 items. Number 1, mechanical waves and electromagnetic waves. Then description in terms of direction of propagation, then I'll be talking about 2 as well. Okay, number 1, transverse waves, and number 2, longitudinal waves. Now, let me take it from the first one. What is mechanical wave? What is mechanical wave? Now, a mechanical wave is not capable of transmitting its energy through a vacuum. A mechanical wave, in other words, we are simply saying that mechanical waves cannot be transmitted not until there is what? A medium. But here I'm using the word vacuum. So what is a vacuum? Simple. Vacuum is where matter does not exist. And when I say matter, I'm also referring to gas, okay? Vacuum is where there is no air. Remember, I explained what matter is all about: solid, liquid, and gas. So where there is no matter, it means there is no air. So mechanical wave is that wave that is not capable of transmitting its energy through a vacuum. But what can it do? Mechanical waves require a medium to transport their energy from one location to another. Example, you have the seismic waves, okay? The seismic waves, you can't do that without a medium. You have sound waves, and this one is very common. I like using examples that are very close by. Sound waves. You cannot transmit sound if there is no medium. In other words, you can't transmit sound without air. That is why there's this experiment we do in the lab, which is called the jar experiment. Placing a bell, electric bell, under a jar, and then you notice that the electric bell will be moving, the hammer will be moving, but the sound is not being heard. Why? Because in that jar is a vacuum. There is no air to transmit the sound. Another example of mechanical waves is wind waves on seas and lakes, okay? And then the last one there is vibration. Of course, vibration is common to anything that has to do with waves. Now let's move to the second one, electromagnetic wave. Remember, I am still trying to describe waves based on what? Material for propagation. I've just explained the first one, and the second one is what? Electromagnetic wave. Now, electromagnetic wave is just the opposite of what? Mechanical wave. Mechanical wave cannot be transmitted, requires material medium. Now, mechanical wave cannot be transmitted through vacuum. So if electromagnetic wave is the opposite, what will it do? That means it's a wave that is capable of transmitting its energy through a vacuum. You see, it's just the opposite of mechanical waves. It can be transmitted through a vacuum. So mechanical wave does not require air, it doesn't require liquid, it doesn't require solid. It can be transmitted, okay? That means it can be transmitted in space, okay? And that is the reason why signals of radio waves in space is possible. You can transmit signal from Earth to space and from space to the Earth because it does not require material medium. Now, electromagnetic waves do not require material medium to transport their energy. I've said that already. Now, they are radiant energy that travels in waves at the speed of light. So whenever you hear the word electromagnetic waves, we are definitely talking about waves that travels with a speed closer to the speed of light. And remember, the speed of light is 300 million meters per second, also written as 3 times 10 raised to power 8. So any wave that travel close to that speed, they are referred to as what? Electromagnetic waves. Then we have some examples here, about 7. Yep, about 7. Number 1 is gamma ray. It's an example of electromagnetic waves. Number 2 is X-rays. Now, I've arranged these in the order of increasing wavelength and decreasing frequency. What do I mean by that? That means gamma ray is the highest in terms of frequency, and radio wave is the longest in terms of wavelength. I will still come back to this, okay? Now, radio waves has the longest wavelength, and that is why it is the only radiation that is used in telecommunication transmission. I will explain that when we get there. So we have gamma rays, we have X-rays, we have ultraviolet light, we have visible light, okay? We have infrared light, we have microwaves, and then finally we have the radio waves. And among these 7 waves here, if you take it from ultraviolet to infrared, these three, they are collectively known as solar radiation. So the solar energy produces these 3: ultraviolet, visible, and infrared. Infrared also refers to what? Heat, thermal energy. Now, let's move on. I want to believe you got that. That was just description based on what? Based on material for propagation. I'm really taking my time to explain and describe what is waves before we move into detail to look at other things like properties and all of that. Now, I want to describe wave based on what? Direction for propagation. Direction for propagation. And I said I'll be using two. So we'll be looking at transverse waves and then we'll be looking at longitudinal waves. Now, what is a transverse wave? Now, a transverse wave is a wave in which the particles of the medium are displaced in a direction perpendicular to the direction of energy transport. Now, let me break that down. Whenever a wave travels in a direction that is at 90 degrees, perpendicular there means 90 degrees to the direction in which it was produced. We don't use the word produce for wave, we use propagation. So once that happens, you simply call it what? Transverse waves. I'll give you an example. For instance, if I'm playing a guitar now, you know, the direction of the bar is this way, horizontally. But how do you play the guitar? You strum vertically, okay? You strum the string vertically. So the direction of propagation is vertically, but yet the wave is traveling horizontally. So whenever you have that scenario, it means the wave is what? A transverse wave. Now, a transverse wave can be created. I like using examples very close by. A transverse wave can be created in a rope. If the rope is stretched out horizontally, okay, and the end is vibrated back and forth. I have a diagram here by my left. As you can see, the rope is tied to the wall and then you have somebody vibrating, you know, moving the rope back and forth. So if you do that, you should be able to create what is called transverse wave. Okay, so if a snapshot of such a transverse wave should be taken so as to freeze the shape of the rope in time, then it will look like the following diagram. Okay, so that is the diagram by my left. If it's possible to take a snapshot while you are, you know, pulling the rope back and forth, this is what you will see. So this diagram you're looking at right now is an example of what? Transverse wave. How is the wave produced? Up and down, up and down. But what is the direction of movement? Horizontally. And that makes it perpendicular, meaning the wave is traveling at 90 degrees to the direction in which it was propagated. Now, on my right is an elaborate diagram of what is happening right here. So this diagram is the representation, graphical representation of transverse wave. Now, as you can see on this diagram, you see where I've marked crest, trough, amplitude, wavelength, rest position, and all of that. I will still come back to this to explain what all of these are represent in wave. All right, let's move on to the next one. A longitudinal wave, that is the second description under direction for propagation. A longitudinal wave is a wave in which the particles of the medium are displaced in a direction parallel to the direction of energy transport. Transverse wave, it was perpendicular to the direction, but longitudinal wave is what? Parallel. That means the angle between the direction of propagation and the transport of the wave is zero. Remember, I said parallel. Parallel lines don't meet, so they don't form an angle. Angle is formed when two lines meet at a point. So longitudinal wave travels parallel. And what are the examples I'm going to show you? A longitudinal wave can be created in a slinky. Slinky here refers to a spring, okay? If the slinky is stretched horizontally, you have the diagram there on the screen. If a slinky is stretched horizontally, what will happen? And the end of the coil is vibrated back and forth in a horizontal direction. Now, the same thing I did for transverse waves. Now, let's do the same thing here. If we take a snapshot of such longitudinal wave, could be taken to freeze the shape of the slinky in time, it will look like the following diagram.